This is a video editorial for the LeetCode weekly contest 488. I'll be explaining my solutions, the solution which I implemented in the order of appearance, and after the editorial you can see me solving these problems live in the live solve section. In my opinion, this contest was like on the easier end, which is why I got a sub 20 minute solve. The wrong answer was because of a minor oversight on my half, but outside of that this contest was fairly easy. So the first problem states that basically for an array I of length n, array nums of length n, we have to count the number of indices such that for the index I, basically it's greater than the average of all the elements to its right. Now since the size of the array is less than or equal to 100, basically what we can do is we can go to every index and then we can find the average of the elements to its right. But like that solution would be O of n square, but we can also solve this in O of n if we iterate from the right end instead. So while iterating from the right, it is also given to us that the last element can never be dominant. So in that case, we iterate from the second last element and we set the suffix sum as this. Now while iterating, we get the count, and also since this is average, we need to the comparison is done using floating point numbers, right? So for making that easier, we can use the double data type. So we get the average like this, and if it's greater, we add it to the answer, and then we increment sum as well. So yeah, this was Q1, fairly straightforward. Q2 was basically like, if you know stack operations, you would instantly solve this. Basically we have to apply this operation repeatedly, and the operation is if two adjacent elements are equal, we have to choose the leftmost such adjacent pair and then replace them with the with their sum, and we have to do this while it's possible, right? So here we can see something like, given an array, assume this is the first possible occurrence of this pair. When this occurrence happens, obviously we'll have to merge this, right? Since the problem states that we have to do this operation on the leftmost possible pair. So after merging this, two things will happen. Either like no operations are possible because of the merge, or the merge will make another operation possible. And if it makes another operation possible, that operation would be either on the right or on the left, or it could be on the both as well, but we have to prioritize the operation on the left, right, since again the problem states that we have to do this on the leftmost pair. Oh my bad. Yeah, in that case we would then merge these two and so on. Here we can see that our merges are going towards the left. The right part is not concerned because of the problem constraints itself. Since we are going toward the left and we are checking our previous operations, this will give some intuition for a stack, right? So yeah, this is that this intuition for the stack was turned out to be correct. Basically what I did was, also we have to return the final array, which also like gave me further intuition for like I could use a vector as a stack itself and then do operations on it. So here basically you push the current element in the result vector, and while its size is greater than 2, we do this check if the last two elements are equal. We do this, which is the operation, else we break, and at the end we return the result vector. So yeah, fairly straightforward. Alright, Q3 was nice. Basically we have to find the number of subarrays with cost less than equal to k, and cost is defined as the maximum, the difference between the maximum and the minimum of the subarray and its length. The cost is defined as the product of the maximum minus minimum of the subarray multiplied by the length of the subarray. So one crucial basically an observation here was, first we observe the function. Obviously as we increase the size of the subarray, the length will increase, right? So that's the first, that's given. But if you look at the left term is max minus min. Let this be of the subarray. As we increase the size of the subarray, max will always go up, right? Since max is monotonically increasing with the size of the subarray, and min will always go down, which means this LHS will always increase with the size of the subarray, and the RHS is also always increasing, which means as we increase the size of the subarray, this cost function will always increase, and this means that the cost function is monotonic with the size of the subarray. And since we have proven that the cost function is monotonic with the size of the subarray, we can use a two-pointer approach here. Basically like two pointer approach is, assume we are at some index, this is j, and this is some index I, this is some valid index I. If this is valid, and since we have proven that the function is monotonic with the size of the subarray, if this is valid, that means every I dash where I dash is greater than I is also valid. It's also valid. Hence, in that case, we basically my overall idea was we are at some index I, index j. We'll be at some index j, and we'll check if I is valid or not. If it is valid, then we'll add it to the answer. We'll add j minus I plus 1, which is the number of subarrays here, right, to the answer. Else we'll move I forward, and we'll keep it moving forward until it stays invalid or I becomes greater than j, in which case it's an invalid subarray, and this will give us 0, which is expected. So now for calculating the cost, what we need to find is first of all the length of the subarray, which is j minus I plus 1, and it can be calculated in constant time. But we also have to find the difference between the max and min of this subarray, right? So during the contest, what I did was I used a sparse table in which would return with the max and min of a subarray in O of 1 time after a n log n pre-computation, which will obviously pass since the constraints are 10 power 5, the values are till 10 power 9, the k value is 10 power 15, and the size of the subarray is, size of the array is 10 power 5. So obviously this would work, but like after the contest I realized that since this problem is just this problem is basically a variation of sliding window maximum or minimum, you could also maintain the subarray maximums and minimums using a monotonic DQ, which is what I implemented after the contest. So during the live portion, you'd see me implement sparse table, and I made a mistake in my template. So, like not in my template, in my implementation of the template. So it took me some time, else I would have solved this instantly. So first I'll show you my sparse table implementation. Here, this is my sparse table template. So basically, yeah, while I is less than equal to j and score is greater than k, which means our condition is invalid, we move I forward. And once it gets broken, once our condition becomes valid, we add this to our answer. And now for calculating the score, this is the length. Sparse table would return us the min and maximum, and we'll multiply this by the length and get our result. And for the monotonic TQ approach, it's the same idea, but this would be O of n, no n log n pre-computation. So this is like if you have done the sliding window max and min problem, this would be trivial. Basically here I am maintaining the monotonicity of both the DQs. Now I am moving the other pointer forward, basically getting the length. Obviously this should be non-empty for this. Getting the mins and maxes, the score, if the score is greater than k, that means invalid, and if the index is there in the DQ, we remove it by pop front. So this would ensure that once, if it's monotonic, this would do the DQ operations and move I forward, else that means our I and j condition is valid, so we break from this loop and we add this to our answer. So yeah, this was Q3. I'd say this required like more knowledge, more ball knowledge than Q4. Q4 was a straightforward DP problem. Like the first thing I did here was look at the constraints where n1 and n2 are less than equal to 100. The values are between 1e6, 1e plus 1e6 and minus 1e6, and k is this min of n1 and 2. Yeah, 1.3k solves. This was fairly easy. And the problem is basically we are given two arrays, nums1 and nums2, and we have to choose k pair of indices such that the product of elements of nums1 I into nums2 j is maximized. So obviously looking at the constraints and the problem statement itself, you could devise some sort of DP idea, right? Where the DP idea would be, assume I am at some I1 for nums1, I2 for nums2, and I have k pairs remaining. So what I would do is either I try to make a pair, in which case I'll go to I1 plus 1, I2 plus 1, and since I've made a pair, this would become k minus 1. And obviously k has to be greater than 0 for this, which is the oversight I did during the contest. This caused a negative index overflow. So either I would transition here, or I would, if this is the case where I'm choosing a pair using I1 and I2, which means since I've made this pair, I'll have to add, basically, let's say n1 was nums, not n1, a1 was nums1, so I'll have to add a1, I1 into a2, I2 to the answer, right? This is for k greater than 0. And obviously otherwise we can always transition, like this is kind of like LCS. Yeah, you could transition to I1, I2 plus 1 and k, which means I have not made a pair using this, and I2 is definitely getting skipped, but I1 might be used in a later answer. And a symmetric operation for this would be I1 plus 1, I2 and k, which is I1 is definitely getting skipped, but I2 might be used in a later operation with obviously k more pairs remaining, since what is this? And here we won't add anything since we are skipping, and obviously k more pairs are remaining since we've skipped this. So yeah, this was my implementation. During the contest, this was the negative indexing error due to an oversight. Here also the array size was like a three state matrix with total size of 1 is 6, right? So I was kind of worried it might MLE because LeetCode stuff. So I declared it globally. This was the recursive idea. Basically, you initialize it to -infinity. Also, instead of initializing it to -1, there is a chance that -1 is a possible answer in the array since the values are negative as well. But we try using -1 as a cache flag, right? So in that case, I just use -infinity, which I know would never be possible. So yeah, the idea is, first of all, the base case. If we reach at the end, if either I1 is equal to N1 or I2 is equal to N2, which means I1 reach the end or I2 reach the end. If we have made all the pairs, since this was exactly k pairs, right? Yeah, this was exactly k pairs. If we have made all the pairs, we return 0, else a negative infinity flag. Also, if like the problem stated that you would make greater than less than equal to k pairs, like at most k, then this condition would not be there. We'll just return 0. And obviously the cache check, if it's not -infinity, we return it. Else we take the values. If k greater than 0, we do the take transition at I1 plus 1, I2 plus 1 and k minus 1. Else the skip operations, where we skip 1, where we go to I1 plus 1 and I2, or we skip 2, where we go to I1 and I2 plus 1, and we take the max and we return all. Yeah, this was it. I'd say this was like way too easy for a force problem, but alright, yeah. And obviously this had bad runtime since it's a recursive solution on a 3-state DP matrix, but you could easily convert this into an iterative solution since the transitions were very simple. Fix the order of iteration, and yeah, either we do the skip transitions, I1 plus 1 or I2 plus 1, or we do, if x is greater than 0, then we do the take operation, where we go here. Alright, yeah. This was my explanation for my implementation of all the 4 problems. And you can see me solving this live in the later section, where yeah, you could see I would have solved this in 3 minutes earlier and this 5 minutes earlier if I had not made silly mistakes, but it is what it is.
ये क्या है? अब हो रहा है।